Today we're going to talk about a Frenchman, philosopher, mathematician, genius named Descartes. And I know it looks like it says Descartes, and here in Kentucky we might want to go with the Descartes, but his name is Descartes. This is a picture of him. He was born in, I believe, 1596. He contributed to a lot of the mathematics that you use today. You know, our XY planes called the Cartesian coordinate plane. Cartesian. All right. If you've ever heard the saying, "I think, therefore I am," Descartes, that's his work in philosophy. And if you take philosophy one day, you'll talk a lot about Descartes. An interesting fact about him is he never went anywhere without his aviator glasses on. You can see in this picture he has them on. He never took them off. Very interesting. So we're going to talk specifically about one of his contributions to math, rule of signs. From time to time we talk about things that are a little bit out of date, just for mathematics' sake. This is one of those. What this rule is going to tell us is if you have a polynomial, what are the possibilities for where it crosses the x-axis? What are its number of positive zeros, negative zeros, and then we've got the imaginary zeros as well. So, you know, you've got polynomials that twist and turn. We're going to talk about this rule is, without looking at it, we're going to be able to tell all possibilities of where it crosses the axis. Now, I say this is a little out of date because you can graph it in your graphing calculator or any website that'll graph, and you can tell exactly what the zeros are. So this isn't even going to tell us what the zeros are, it's just going to give us possibilities. But it's cool and it uses the mathematics, so we're going to talk about it. And you're going to do it in pre-cal. Okay. Here's the rule. The number of positive zeros less than or equal to the number of sign reversals in f of x. Negative zeros is less than or equal to the number of sign reversals in f of negative x. And both of them have the same parity, meaning if you get a 4, you can only have 4, 2, or 0. If you get a 3, you can only have 3 or 1. You're going to count down by 2s, making sure that it stays even or odd. That's what the parity is. So let's start by counting up the number of sign reversals in f of x. This is our function. It is a negative 5th degree, and we need to see how many sign reversals there are. And a sign reversal just means it went from minus to plus. So there's 1. It looks like we just have 1 sign reversal. So there's 1, which means our positive zeros can really only be 1. Okay, so next what we need to do is find f of negative x. Which means we're going to replace all of our x's with negative x's. What you'll notice is in the odd terms, like negative x to the 5th, when that x becomes negative x, we get negative x to the 5th. Negative x to the 5th is negative x to the 5th. You know what I mean? Negative x to the 5th turns out to be negative because we have 5 negative signs. But then the negative sign originally makes the whole term positive. So we get x to the 5th. Long story short, what's going to happen is the even terms, the 4, the 2, those are going to stay the same because if you replace x with negative x, the even power, the even exponent cancels out all the negatives. The odd ones are going to change. So negative 7x to the 4th is going to stay the same. Plus 5x cubed is going to become minus 5x cubed because we had 3 x's. If they all turn into negative x's, we get a negative sign. Plus 11x squared minus 2x plus 5. So if you wanted to speed it up, you could just, you don't really have to substitute it in. You just go through and change all of your odd exponent terms. All right, so at most we have one positive 0. Let's check out negative zeros. This thing has one sign reversal because I went from plus x to the 5th to minus 7x to the 4th. I stayed negative to my next term. Another sign reversal, another, and another, because I went minus to plus, to minus, to plus. So I have sign reversals in f of negative x is 1, 2, 3, 4. Okay, so now back up to our rule in yellow. What we're going to end up making is a little table that lists the possibilities. Positive zeros is less than or equal to the number of sign reversals in f of x. Okay, so what we want to come up with is a little chart that has possibilities for positive, negative, and I'm just going to go I for imaginary. The thing about this is we have to have 5. This is a 5th degree polynomial, which means it's going to have 5 zeros. They might be 5 real zeros. They might be, I don't know if we could have all imaginary zeros because it's a negative x to the 5th, which means, think about that, it has to, whatever it does, it has to start at the top left and end at the bottom right. So we're going to have at least one real. And if it has 5, and imaginaries always come in conjugate pairs, we definitely have to have at least one real, because we're either going to have 2, 4, or 0 imaginaries. Okay, so let's go back to our first rule. Sign reversals in f of x, which we found to be 1. The number of positive zeros is less than or equal to that. So we might have one positive 0. If that's the case, then there are no other options, because it has to have the same parity, the same even or oddness. So I might have one positive 0. I can't have 0 because that wouldn't be the same even or oddness. I can't have any more than 1. So I have only one option, which is one positive 0. So what options for negatives and imaginaries do we have? Well, for negative, I had 4 sign reversals, which means the negative column either needs to be 4, 2, or 0. So I might have 1, 4, and 0. That adds up to 5, right? That fits all my rules. 1 or less plus, 4 or less minus, and the rest imaginary. What else could happen? I could have 1, 2, 2. It's a possibility, right? That would be adding up to 5. I haven't violated either of my 2 rules. I have 1 or fewer in the plus column. I have 4 or fewer in the minus column. I have only the same even or oddness, and I add up to 5. Any other options? Why didn't I think about that. Why did I not go 1, 3, 1? Well, the negative column has to have the same parity. If I start at 4, there's no way that I can have 3. And also, imaginaries are always in conjugate pairs. So that's not an option. The only other option, it looks like, would be 1, 0, and 4. All right? So just a quick sketch of what these could look like. 1 positive and 4 negative. Maybe that would look like this. Negative, 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 positive. All right, it's 5th degree. It starts at the upper left, ends to the bottom right. I could have one positive, 2 negative, 2 imaginary. How about that? Negative, negative, positive, and then the other 2 don't show up because they're imaginary. Or Finally, I could have 1 positive, 4 imaginary. That would look something like that. It only crosses the axis 1 time over on the positive side. All right. So the answer to this question lists the possible numbers of positive, negative, and imaginary roots is right there. Those are our possibilities. Just so we can see which one it is, let's go to a picture. Not Mike and Mike. Here is the actual graph. It dips way down low over here on the negative side, but I have 2 real negative roots, and I have 1 real positive root, and the other 2 would be imaginary. They're not x-intercepts, but they're complex numbers involving I that when subbed into the equation wouldn't make it true, would give you 0. Okay? All right, so that's Descartes' rule. Genius, philosopher, Frenchman, 1596, aviator glasses. Descartes out.